Vorticity and Irrotationality. The assumption of zero fluid angular velocity or irrotationality is a very useful simplification. Here we show that angular velocity is associated with the curve of the local velocity vector. Angular velocity. The differential relation for deformation of fluid element can be derived by the examined in this picture, where two fluid lines AB and AC, which deformed to AB prime to CB prime, the first position of A, example here, and C here. Initially perpendicular at the time t, move and deform so that t plus dt, they have slightly different lengths A prime, B prime, and B prime, C prime, as shown in this picture, also in these two lines. Such a deformation occurs kinematically because A and B and C have slightly different velocities when the velocity field V have spatial gradient. All these differential change in the motion of A, B, and C are noted in the picture. We define the angular velocity omega z, velocity of an element of a fluid equals to the average of the angular velocity of each line clockwise. So we can write omega z equals to, we have a clockwise rotation here, which the angular velocity is d beta on dt minus, this is the unclockwise, d alpha on d average. So we have a relation for the angular velocity about z, which is from this picture. We can also calculate the each angle in the picture. Let me write here. For d alpha we have tangent inverse on d on ln x on the plus dt. We make a limitation on the tangent. We have d alpha equals to limit dt to 0, tangent inverse there plus dx one plus from u ln x dt equals to the quantity is smaller than 2 smaller than 1 and is eliminated from our limitation, and the result is the expression of b dt. And for d beta also we have limitation dt equals to 0. In the d beta from the picture we can calculate the d beta equals to the amount of the front side to the side of the angle d beta. So we can write the round u on round phi dy dt plus dy plus round v on round y dy dt. As same as previous, this quantity, this part of the relation in this equation is smaller than dy, and the result is round u on round y dt. So we have two relation for the velocity, angular velocity components, and now we can write the relation for angular velocity related to the velocity vector components. Let me write in the next page. Omega z equals to half of and we have d alpha equals to and d beta equals to with replacing to the angular velocity we can obtain a relation for angular velocity for in the around z direction, and in the exactly similar we can obtain for the y, x and y direction. So we have these three relations. In the y direction, around y and around x we have the relation for now we have a relation for angular velocity vector as omega equals to omega xi, omega yj, and omega zk. And we know we can define the vorticity as curve for the definition of angular velocity also, which is a matrix form of UVW. Since the factor of half is annoying, many workers prefer to use a vector twice as large, called the vorticity, as the function zeta equals to, so we have this, the angular velocity, and the vorticity is zeta equals to curve V. Many flows have negligible or zero vorticity and called the irrotational or irrotational flows. Vorticity equals to 0 or curve V equals to 0. These relations are useful to have a description for shear stress rate that will be discussed in the next chapters. This is the end of this section, and this next section is the frictionless irrotational flows.